The United States Army on December 7, 1941, numbered 1.6 million soldiers. By comparison, the Wehrmacht fielded 3.8 million troops for Operation Barbarossa in June 1941. The U.S. Navy counted 284,000 sailors. President Franklin Roosevelt's directive called for rapid expansion to 8 million Army personnel, 2 million Navy sailors, and 400,000 Marines by December 1943. This mobilization timeline, 24 months, exceeded the Civil War's entire 4-year recruitment total. The logistical implications defied conventional military planning. The War Department's internal memoranda from January 1942, declassified in 1975, reveal the magnitude of concern among senior planners. General Brahan B. Somerville, commanding the Army Service Forces, calculated that traditional construction approaches would consume 48 million board feet of lumber monthly, approximately 1/4 of total U.S. timber production at 1941 levels. This demand would compete directly with shipbuilding programs requiring massive timber quantities for cargo vessel construction, aircraft production needing spruce and balsa for airframe components, and civilian housing construction for defense workers flooding into industrial centers. Housing represented the first crisis. Traditional military barracks construction followed engineering standards established by the U.S. Army Corps of Engineers in 1918. Specifications required concrete foundations extending below the frost line, dimensional lumber framing with specific grade requirements, slate or asphalt shingle roofing, and copper plumbing throughout. Construction timelines averaged 6 weeks per building for specialized crews working under optimal conditions. Weather delays, material shortages, or labor unavailability extended these timelines considerably. The mathematics proved impossible. 8 million soldiers required approximately 400,000 barracks units at 20 men per building. 6-week construction timelines meant completing 6,667 barracks monthly, requiring 40,000 skilled carpenters, plumbers, and electricians working simultaneously. The United States construction industry in 1941 employed roughly 1.2 million workers total, including residential, commercial, and infrastructure projects. Diverting tens of thousands to military construction would halt civilian building nationwide. Moreover, the construction workforce itself required training, supervision, and housing. Building barracks for soldiers required housing construction workers, creating a circular dependency that multiplied infrastructure demands. Each major base required not just facilities for military personnel, but also housing for civilian construction workers, contractors' offices, material storage yards, and transportation infrastructure for moving supplies. Geographic distribution compounded the crisis. The War Department identified critical base locations based on strategic requirements and operational planning. Staging areas in England for eventual European invasion, naval facilities in Pearl Harbor requiring reconstruction after Japanese attack, air bases in India and China for bombing campaigns against Japanese home islands, defensive positions throughout Alaska's Aleutian island chain, training camps across the continental United States for newly inducted soldiers, forward supply depots in Australia supporting Southwest Pacific operations, communications facilities in Greenland and Iceland for Atlantic convoy protection. Each location presented unique challenges beyond simple construction. England required air bases capable of housing 150,000 8th Air Force personnel while integrating with existing Royal Air Force infrastructure and operating under wartime blackout conditions. North Africa needed desert-capable facilities for Operation Torch landings, scheduled for November 1942, where daytime temperatures exceeded 120 degrees Fahrenheit and sandstorms could strip paint from vehicles overnight. Pacific Island bases demanded structures resistant to typhoon winds exceeding 150 miles per hour, rainfall measuring 200 inches annually, and salt air corrosion accelerating metal deterioration. Aleutian positions needed insulation for temperatures reaching 40 degrees below zero Fahrenheit, construction methods compatible with permafrost conditions, and anchoring systems resisting hurricane-force winds occurring weekly. Traditional construction methods required local material sourcing, impossible on remote Pacific atolls, lacking forests, quarries, or manufacturing facilities. Shipping conventional building materials consumed precious cargo space needed for weapons, ammunition, food, fuel, and vehicles. A single traditional barracks consumed approximately 30,000 pounds of materials, 12,000 board feet of dimensional lumber weighing 20,000 pounds E8. Zero bricks or concrete blocks at 4,000 pounds, 2,000 square feet of roofing material at 3,000 pounds, plus windows, doors, plumbing fixtures, electrical components, and hardware. Liberty ships carried 10,000 tons capacity. Dedicating one ship to barracks materials provided components for only 667 buildings. The crisis extended beyond housing. Medical facilities required sterile environments, temperature control for medication storage, specialized equipment mounting for surgical theaters, and X-ray machines, and isolation wards for contagious diseases. Maintenance shops needed clear-span interiors for aircraft and vehicle repair, overhead crane systems for engine removal, ventilation for welding operations, and secure parts storage. Command centers required secure communications infrastructure, map rooms with plotting tables, cryptography facilities with electrical power backup, and briefing spaces for large staff meetings. Storage depots needed rodent-proof, weather-resistant structures for ammunition, requiring temperature and humidity control, food storage with refrigeration, medical supplies maintaining sterility, and spare parts protection from corrosion. Each facility type demanded different construction specifications, different materials, different trades, and different timelines. A hospital required plumbing and electrical systems far more complex than barracks. A maintenance hangar needed structural engineering calculations for clear spans exceeding 100 feet. An ammunition depot required explosion-resistant construction with earth berms and controlled access. Multiplying these specialized requirements across hundreds of locations created planning nightmares. Lieutenant Colonel Burton W. Chelberg, assigned to the Quartermaster Corps Construction Division in February 1942, later testified before congressional committees, "We calculated that conventional construction methods would require until 1947 to complete basic infrastructure for planned force levels. The war would end one way or another before we finished building places to house soldiers." His testimony, entered into congressional record on March 15, 1946, documented the crisis that drove American planners toward radically different solutions. The situation demanded innovation. Traditional approaches, proven over decades of peacetime military construction, couldn't scale to wartime demands. The U.S. military needed a construction revolution, not an evolution. That revolution arrived from an unexpected source: a private construction company in Rhode Island facing similar challenges on a Navy contract. The German Wehrmacht approached military construction with engineering precision refined over decades. Prussian military architects in the 1870s established standardized barracks designs following defeat in the Franco-Prussian War. These specifications, updated through World War I and the Weimar period, governed Wehrmacht construction beginning in 1935 during rearmament under the Nazi regime's expansion programs. The standard Type B barracks, designated Mannschaftsgebäude in Wehrmacht documentation, measured 150 feet long by 30 feet wide, providing 4,500 square feet of interior space. Concrete foundations extended 3 feet below grade, poured according to specifications, requiring minimum 3,000 psi compressive strength. Timber framing used 6x6-inch posts, spaced 12 feet on center, connected by 2 and 10-inch joists and rafters. Exterior walls consisted of brick or concrete block with plaster finishing. Brick preferred in Western Germany, where clay deposits enabled local manufacturing, concrete block in eastern regions, where brick production proved less economical. Roofing employed slate tiles over timber sheathing, slate quarried primarily from Thuringian deposits, providing roofing material considered virtually indestructible. Interior partitions divided space into sleeping quarters for 96 enlisted men arranged in bunks, separate NCO rooms providing privacy for sergeants, a day room for recreation and off-duty activities, latrine facilities with running water and sewer connections, and storage rooms for unit equipment and personal belongings. Construction required specialized crews organized following traditional German building trades. 4 journeyman carpenters holding official certification from trade guilds, 2 master masons with minimum 5 years post-apprenticeship experience, 2 roofers experienced in slate installation techniques, 1 master electrician certified for commercial installations, 1 journeyman plumber trained in copper pipe soldering and steam heating systems. Supporting this skilled corps, 10 general laborers handled material movement, excavation and cleanup operations. Material requirements included 12,000 board feet of lumber, graded for structural use, 8,000 bricks or equivalent concrete block, approximately 80,000 pounds, 2,000 square feet of slate roofing, weighing 9,000 pounds, copper piping for plumbing systems totaling 400 linear feet, electrical wiring with ceramic insulation covering 2,000 linear feet, iron radiators for steam heat, 16 units weighing 200 pounds each, window assemblies, 24 units with double-glazed glass, door assemblies, 8 exterior doors, 12 interior doors, and hardware including hinges, locks, nails, screws and fasteners. Total construction time averaged 6 weeks assuming favorable weather conditions, defined as temperatures above freezing, precipitation below 1 inch weekly, and winds below 20 miles per hour. These ideal conditions rarely occurred simultaneously for 6 consecutive weeks, particularly during winter months when construction essentially halted across northern Europe. Realistic timelines accounting for typical weather delays extended to 8 or 10 weeks. Cost per unit stabilized at 55,000 Reichsmarks in 1940, approximately $15,000 at contemporary exchange rates of 3.67 Reichsmarks per dollar. This figure represented direct construction costs only, excluding foundation excavation charged separately, utility connections to water, sewer and electrical infrastructure, interior furnishings including bunks, lockers, tables and chairs, and landscaping or site improvement. Complete facility costs, including all ancillary expenses, approached 75,000 Reichsmarks. Adjusted for inflation, each Wehrmacht barracks cost approximately $280,000 in 2024 dollars. The Wehrmacht's methodical approach produced durable structures meeting exacting standards. Barracks built in 1936 for Luftwaffe training facilities in Bavaria remained operational throughout the war without major repairs. Their solid construction provided excellent insulation against winter cold, important for Germany, where winter temperatures routinely dropped below freezing. Brick walls offered superior sound dampening compared to lighter construction, improving soldier comfort in crowded quarters. Slate roofs proved fireproof, critical for facilities storing ammunition and fuel. The substantial construction withstood limited combat damage. Brick walls resisted small arms fire and shell fragments better than lighter materials. However, the system's rigidity created problems as the war expanded beyond initial planning assumptions. The Soviet winter offensive in December 1941 caught German forces in inadequate shelter across the entire Eastern Front. Temperatures plummeted to -40 degrees Fahrenheit in frontline positions. Wehrmacht after-action reports documented severe frostbite casualties among troops lacking proper housing. Entire infantry companies suffered 30–40% casualties from cold exposure alone. Army Group Center reported 228,000 frostbite cases between December 1941 and March 1942, exceeding combat casualties for the same period. Construction materials froze solid under these conditions. Concrete wouldn't cure below 40 degrees, without expensive additives and heating equipment unavailable on the Eastern Front. Lumber became brittle at extreme temperatures, causing structural failures during assembly. Mortar froze before achieving proper bonding between bricks. Ground frost extended 6 feet deep, making foundation excavation nearly impossible without industrial equipment. Construction crews worked in conditions approaching impossibility, attempting to build permanent structures in weather that prevented basic construction activities. Wehrmacht construction doctrine called for adapting barracks designs to local conditions, but this flexibility existed more in theory than practice. Each design modification required new blueprints prepared by certified architects, different materials sourced through supply channels already strained, and specialized construction knowledge possessed by limited personnel. The centralized Wehrmacht construction bureaucracy, headquartered in Berlin, struggled coordinating projects across thousands of miles, with communication systems disrupted by partisan activity and Soviet air raids. North African operations presented opposite environmental challenges. The Africa Corps, deployed to Libya in February 1941 to support Italian forces, faced 130-degree desert heat during summer months. Traditional barracks designs with heavy insulation and minimal ventilation proved uninhabitable. Interior temperatures exceeded 140 degrees. Soldiers suffered heat exhaustion even while resting indoors. Wehrmacht engineers modified specifications for desert conditions, removing insulation layers, adding ventilation louvers, using lighter materials reducing heat absorption. Each modification required approval through bureaucratic channels. Shipment of specialized materials across Mediterranean supply lines threatened by British naval and air forces, and retraining construction crews in unfamiliar techniques. By 1942, material shortages affected Wehrmacht construction throughout occupied Europe. Timber came from Norwegian forests, Polish woodlands and Romanian mountains, each source requiring different transportation logistics. Cement production couldn't meet military and civilian demands simultaneously. Copper for plumbing disappeared into ammunition production. Steel reinforcement went to fortification construction along the Atlantic Wall. Construction timelines stretched from 6 weeks to 12 weeks, then longer. A barracks begun in January 1943 might not reach completion until April. Wehrmacht quartermaster records documented projects abandoned half-finished when construction crews received orders for new assignments. The methodical engineering that produced excellent buildings in peacetime became a liability in total war's chaos. The Quonset hut originated not from military engineers, but from the private sector. In early 1941, before Pearl Harbor, the U.S. Navy Bureau of Yards and Docks issued contracts for rapid base construction at naval facilities being expanded under the Two-Ocean Navy Act of 1940. The Davisville Naval Construction Battalion Center in Quonset Point, Rhode Island, required housing for 25,000 personnel by summer 1941. George A. Fuller Construction Company of New York received the Quonset Point contract in March 1941. Their chief engineer, Otto Brandenberger, analyzed the timeline. Traditional barracks construction couldn't meet the Navy's compressed schedule. Brandenberger's team studied British Nissen huts, semicircular corrugated steel structures developed during World War I. The Nissen design offered rapid assembly, but suffered from poor insulation, inadequate ventilation, and structural weakness in high winds. Brandenberger redesigned the concept. His specifications called for standardized steel arch sections, manufactured to precise tolerances, bolted assembly requiring no welding or specialized tools, integrated plywood interior lining for insulation, end walls framed in timber with standard doors and windows, and foundation systems adaptable to various soil conditions without extensive excavation. The prototype Quonset, assembled in May 1941, measured 20 feet wide by 48 feet long. The semicircular cross-section provided 960 square feet of usable interior space, enough for sleeping quarters for 24 enlisted men or office space for 12 administrative personnel. The entire structure weighed 6,800 pounds and consisted of components small enough for 2 men to carry. Assembly required no specialized skills. The Navy tested assembly using untrained sailors, following written instructions and photograph sequences. A 6-man crew erected the first test structure in 37 hours. After minor design modifications improving the bolt pattern and panel alignment, assembly time dropped to 16 hours. Cost analysis revealed dramatic advantages. Material costs totaled $800 per unit for steel, lumber, and hardware. Manufacturing labor added $200. Total cost $1,000 per building compared to $15,000 for conventional barracks, a 15-fold savings. These figures caught immediate attention from Navy planners, confronting expansion budgets exceeding $200 million for facilities alone. The Navy Bureau of Yards and Docks tested prototypes through summer 1941. Engineers subjected Quonsets to simulated hurricane winds, artificial snow loading, and extreme temperature cycling. The curved steel structure proved remarkably resilient. The arch shape naturally shed wind loading. Snow and rain ran off without accumulation. The steel panels expanded and contracted with temperature changes without structural failure. After Pearl Harbor in December 1941, the War Department's Construction Division received authorization to adopt the Quonset design for Army use. Specifications were finalized in February 1942. The Army Quartermaster Corps issued contracts to multiple manufacturers: Great Lakes Steel Corporation in Detroit, Strand Steel Corporation in Louisville, Pacific Coast Building Products in California, and 10 other companies by June 1942. Manufacturing proved straightforward. Steel mills rolled corrugated panels to specification. Fabrication shops cut panels to length, punched bolt holes, and packaged complete building kits. No complex machining or precision tolerances required, just basic metalworking equipment available in any industrial facility. This simplicity enabled rapid production scaling. The standardized design facilitated mass production. Every Quonset used identical components, regardless of manufacturer. Panels from Detroit fit structures assembled in Australia. This interchangeability proved critical for replacement parts and field repairs. Damaged sections could be unbolted and replaced without specialized tools or expertise. By December 1942, monthly Quonset production exceeded 3,000 units. By December 1943, 8,000 units monthly. Peak production in 1944 reached 12,000 Quonsets per month from 14 manufacturers operating across the United States. Total war production ultimately reached 160,000 units before manufacturing ceased in September 1945. Direct comparison of American and German military construction reveals fundamental differences in engineering philosophy and strategic priorities. The Wehrmacht emphasized durability and permanence. The US military prioritized speed and adaptability. These divergent approaches produced measurably different outcomes across multiple dimensions. Construction timeline: Wehrmacht. Type B barracks required 6 weeks minimum with specialized crews working favorable conditions. Weather delays, material shortages, or labor shortages extended timelines to 12 weeks or longer by 1943. Quonset huts required 16 hours with 6 untrained personnel, approximately 250 times faster than German construction. Material requirements: German barracks consumed 30,000 pounds of lumber, brick, concrete, and roofing materials per building. Quonset huts used 6,800 pounds of steel and plywood. The weight difference, 23,200 pounds, represented critical cargo capacity savings. One Liberty ship carrying Quonset components could transport materials for 1,270 buildings versus 333 German-style barracks. Transportation logistics: Wehrmacht construction materials required multiple cargo vehicles. Lumber came in various dimensions, requiring careful loading and unloading. Bricks shipped on pallets. Roofing tiles needed careful handling to prevent breakage. A complete barracks required approximately 6 truckloads. Quonset components packed efficiently. One complete building fit on one truck. Shipping containers stacked arch sections nested inside each other, maximizing cargo density. Labor requirements: German construction demanded skilled tradesmen. Carpenters understanding timber framing, masons laying brick, roofers installing slate tiles, electricians running conduit, plumbers soldering copper pipe. These specialists represented scarce resources. The Wehrmacht's construction corps competed with combat engineering units and occupation forces for qualified personnel. Quonset assembly required 6 people capable of reading instructions, operating hand tools, and turning wrenches. No specialized training necessary. Infantry units assembled their own housing. Cost analysis: Wehrmacht barracks cost 55,000 Reichsmarks, $15,000, in direct construction expenses. Quonset huts cost $1,000. The $14,000 difference per building funded significant military equipment: 3 M4 Sherman tanks, $4,500 each, or 5 Willys MB Jeeps, $2,800 each, or complete individual equipment for 75 infantrymen, $185 per soldier. Across 160,000 Quonsets built, American cost savings totaled $2.24 billion, equivalent to 30,000 Sherman tanks. Durability and lifespan. German barracks built in 1936 remained serviceable in 1945 and beyond. Brick construction, slate roofing, and concrete foundations provided century-long service life. Quonset huts, designed for 5-year military service, often lasted decades but eventually succumbed to rust and structural fatigue. However, wartime utility mattered more than peacetime longevity. Structures needed to last until victory, not into the next century. Climate adaptability. Wehrmacht engineers modified barracks designs for each climate zone: insulation for Russian winters, ventilation for North African summers. Each modification required new blueprints and different materials. Quonset designs remained standardized. The same basic structure served in Alaska and New Guinea. Interior adaptations, added insulation for Arctic, increased ventilation for tropics, used modular components without changing the fundamental structure. Maintenance requirements. German barracks needed continuous upkeep. Timber required treatment against rot and insects. Roofs needed regular inspection and tile replacement. Plumbing systems froze in winter without proper draining. Electrical systems required qualified electricians for repairs. Quonset huts proved remarkably low maintenance. Steel resisted rot and insects. The curved roof shed water and snow naturally. No plumbing meant no frozen pipes. Electrical systems ran through surface-mounted conduit, requiring minimal expertise for repairs. Battlefield survivability. Both structures offered minimal protection against direct artillery hits. However, Quonset huts proved more resilient to nearby explosions. The flexible steel construction absorbed blast overpressure better than rigid brick walls. A near miss that cracked masonry walls requiring extensive repairs might only dent Quonset panels, easily replaced by unbolting damaged sections and installing spares. The accumulated differences produced strategic effects, visible in operational tempo and force deployment patterns. The Pacific War's island-hopping campaign presented unique construction challenges. Each captured island required rapid base development, sometimes within days of Marines securing beachheads. Traditional construction methods were impossible. Quonset huts became essential infrastructure. Guadalcanal Campaign, August 1942, February 1943. The 1st Marine Division landed on Guadalcanal August 7, 1942. Initial shelter consisted of canvas tents in tropical climate, averaging 200 inches annual rainfall. Within 3 weeks, equipment suffered severe rust damage, medical supplies spoiled, ammunition deteriorated. The situation demanded permanent structures immediately. The first Quonsets arrived by cargo ship in September 1942. CB construction battalions, the Navy's construction battalions, formed specifically for rapid base building, assembled them in hours. Medical Quonsets with added insulation and sterile interiors housed field hospitals. Storage Quonsets protected ammunition and supplies from humidity. Maintenance Quonsets provided covered workspace for aircraft and vehicle repair. By November 1942, Henderson Field possessed over 200 Quonset structures supporting aviation operations. New Guinea Campaign, 1943 to 1944, General Douglas MacArthur's Southwest Pacific Advance, required air bases every 300 miles supporting leapfrog operations. Each new airfield needed complete infrastructure within weeks of Army occupation. Milne Bay, Dobodura, Nadzab, Hollandia, each base grew from jungle clearing to operational facility, using Quonsets as primary structures. The 871st Engineer Aviation Battalion's report from Hollandia in May 1944 documented receiving 150 Quonset kits by cargo ship 3 days after infantry secured the area. Within 72 hours, the battalion erected housing for 2,000 personnel, maintenance facilities for 60 aircraft, and supply depots protecting 500 tons of equipment. Traditional construction would have required months, time MacArthur's operational tempo couldn't afford. Marianas Campaign, June-August 1944. Saipan, Tinian, and Guam provided bases for B-29 Superfortress bomber attacks on Japanese home islands. Each B-29 group required massive support infrastructure, maintenance hangars for complex aircraft systems, briefing rooms for air crews, communications centers coordinating missions, medical facilities for wounded airmen, supply depots for specialized ordnance. The 20th Air Force constructed facilities using thousands of Quonsets. Philippines liberation, October 1944, August 1945. MacArthur's return to the Philippines required base development across multiple islands. Leyte, Luzon, Mindoro, each needed port facilities, supply depots, hospitals, and airfields. The 6th Army's logistics report documented over 8,000 Quonset structures erected in the Philippines between October 1944 and war's end. These buildings supported forces eventually exceeding 300,000 personnel preparing for planned invasion of Japan. Logistics data reveals Quonset deployment's strategic impact. A Liberty ship departing California carried approximately 300 Quonset kits. The round-trip voyage to the Philippines averaged 40 days. Each ship delivered housing and facilities for 7,200 personnel or equivalent storage, maintenance, and medical facilities. German-style construction would have required approximately 6 ships carrying 2 million pounds of conventional materials to support similar force levels, occupying shipping capacity needed for ammunition, food, and fuel. The Pacific Theater consumed approximately 60,000 of the 160,000 Quonsets produced during the war. These structures enabled the rapid base expansion necessary for island-hopping strategy's success. Without Quonsets, MacArthur's advanced schedule would have required dramatic slowdown awaiting traditional construction completion. The European theatre required different construction approaches. England possessed existing infrastructure, industrial capacity, and construction labor, advantages absent in Pacific Islands. Nevertheless, Quonsets proved essential for rapid facility expansion. United Kingdom build-up, 1942-1944. The 8th Air Force deployment required housing and support facilities for eventually 300,000 personnel operating 2,000 heavy bombers. Traditional British construction methods couldn't meet expansion timelines. The U.S. Army Transportation Corps shipped 30,000 Quonset kits to England between January 1942 and June 1944. These structures appeared at airfields across East Anglia, barracks for bomber crews, briefing rooms for mission planning, operations centers coordinating 1,000-plane raids, maintenance facilities for aircraft repair, hospitals treating wounded airmen. The 305th Bomb Group at Chelveston assembled 200 Quonsets between August and December 1942, transforming a grass airfield into fully operational heavy bomber base within 4 months. North African Campaign, November 1942, May 1943. Operation Torch landings in Morocco and Algeria required immediate base infrastructure. French colonial facilities proved inadequate for American force levels. The WWII Corps established headquarters at Tebessa, Algeria, using Quonset structures for command centers, communications facilities, supply depots, and medical installations. Desert conditions tested Quonset adaptability. Daytime temperatures exceeded 120 degrees Fahrenheit. Sand infiltrated everything. Water remained scarce. Standard Quonsets with added ventilation and reflective paint on steel panels performed adequately. Units added canvas sunshades and wet burlap wall coverings for evaporative cooling. Improvised modifications addressed desert challenges without requiring fundamental design changes. Italian Campaign, September 1943, May 1945. The invasion of Italy required base development on captured territory lacking infrastructure. Allied forces constructed facilities at Foggia, Naples, and Livorno using Quonsets for primary structures. The 15th Air Force operated 1-200 heavy bombers from Italian bases by early 1944, all supported by Quonset maintenance facilities, supply depots, and housing. Sicily presented particular challenges. The 1st Infantry Division landed July 10, 1943, and required immediate facilities for wounded supplies and equipment. Cargo ships offloaded Quonset kits directly onto beaches. Engineer battalions assembled structures within artillery range of German positions. Medical Quonsets treated casualties within 48 hours of landing, far faster than traditional hospital construction allowed. Normandy invasion and advance, June 1944, May 1945. D-Day preparations included pre-positioning Quonset kits for rapid deployment following invasion. The first Quonsets went ashore on Omaha Beach, June 8, 1944, 2 days after initial landings. Engineer units assembled field hospitals, supply dumps, and command posts, while combat units pushed inland. As Allied armies advanced across France, Quonset construction followed. Each new supply depot, each field hospital, each maintenance facility used standardized Quonset components. The Third Army's logistics trains carried Quonset kits alongside ammunition and fuel. When Patton's forces paused for resupply, engineer units erected facilities within hours. The rapid construction capability enabled operational flexibility. Traditional construction would have anchored supply infrastructure to permanent locations, limiting advance speed. Quonsets allowed mobile logistics, facilities erected, used, and abandoned as operations demanded. This mobility proved critical during the Ardennes offensive in December 1944, when American forces rapidly relocated supply depots and medical facilities to support counterattacks against German breakthrough. European theater deployment totaled approximately 45,000 Quonsets, supporting operations from England to Germany. These structures enabled the massive logistical infrastructure required for Allied victory in Europe. While Pacific and European theaters consumed most military attention, secondary theaters presented equally challenging construction requirements, often overlooked in popular histories. Aleutian Islands Campaign, June 1942, August 1943. Japanese forces occupied Attu and Kiska Islands in June 1942, the only American territory captured during World War II. U.S. response required base construction throughout the Aleutian chain in Earth as most hostile weather. Constant winds exceeding 100 miles per hour, annual precipitation over 60 inches, temperatures dropping to -40 degrees, and zero visibility fog weeks at a time. The 807th Engineer Aviation Battalion constructed bases at Adak, Amchitka, and Shemya Islands using Quonsets as sole permanent structures. Traditional construction was impossible. Permafrost prevented foundation excavation, constant wind made conventional framing impractical, and shipping conventional materials to islands 1,500 miles from anchorage proved prohibitively difficult. Quonsets proved remarkably successful in Arctic conditions. The curved structure shed wind naturally. Anchored to permafrost using steel stakes and guy wires, Quonsets survived hurricane-force winds that destroyed conventional structures. Interior insulation and heating stoves provided adequate warmth. By May 1943, American forces operated from facilities that didn't exist 6 months earlier, forcing eventual Japanese evacuation of Kiska. China-Burma-India Theater, 1942-1945. The CBI theater presented unique challenges: vast distances, minimal infrastructure, hostile climate, and complete isolation from conventional supply lines. All materials arrived by air over the Himalayan hump or via convoy through Burma's jungle roads. American air bases in Kunming and Chengdu required facilities for B-29 operations against Japanese targets. Quonsets arrived disassembled in C-46 cargo aircraft, the only practical delivery method given terrain and distance. Chinese labor under American engineer supervision assembled structures from air-delivered components. By January 1945, B-29s flew combat missions from bases built entirely with Quonset infrastructure. The India-based 10th Air Force operated from facilities at Chabwa and Jorhat using similar Quonset construction. Monsoon conditions, 200 inches annual rainfall and 100-degree temperatures, tested structures to limits. Rust proved constant enemy requiring aggressive maintenance. Nevertheless, Quonsets proved more practical than conventional construction in jungle conditions, where timber rotted within months and masonry crumbled from humidity. Persian Corridor, 1942-1945. The Persian Corridor supply route delivered American Lend-Lease aid to Soviet forces fighting Germany. Supplies shipped to Iranian ports, transported overland via truck convoy and railroad to Soviet border. American military personnel operated this logistics pipeline, requiring bases throughout Iran. The Persian Gulf Command established facilities at Abadan, Tehran, and along rail corridors using Quonsets adapted for desert conditions. Summer temperatures exceeded 130 degrees. Conventional barracks would have required extensive cooling, impossible given power limitations. Quonsets with maximum ventilation and reflective exterior coatings provided adequate shelter. These secondary theaters collectively employed approximately 15,000 quonsets, a relatively small fraction of total production, but absolutely critical for operations in regions where conventional construction proved impractical or impossible. August 1945 brought victory and an immediate question: what happens to 160,000 military structures scattered across 46 countries and every American state? The Surplus Property Act of 1944 provided the answer, transforming military assets into civilian infrastructure and inadvertently shaping post-war American development. Veterans returning home under the GI Bill flooded universities beyond capacity. Existing dormitories and classrooms couldn't accommodate enrollment increases exceeding 500% at major institutions. Universities purchased surplus Quonsets by thousands. The University of Wisconsin erected 150 Quonsets in 1946, housing 2,000 students in what became known as Badger Village. UCLA's Vetville consisted of 300 Quonsets providing married student housing. Similar installations appeared at Yale, Michigan, Stanford, and dozens of other schools. These temporary structures often remained decades. Wisconsin's Quonset Village operated until 1968, 22 years. Many students later recalled Quonset life as formative experience, creating tight communities in circumstances all shared. The structures proved adequately comfortable, surprisingly durable, and infinitely better than no housing at all. Agricultural adoption proceeded even more extensively. Farmers recognized Quonset's utility for machinery storage, grain drying, and livestock shelter. The curved roof shed snow naturally, critical for northern climates. Steel construction resisted rot, insects, and fire. The clear span interior required no support posts, allowing unobstructed tractor and combine access. An estimated 40,000 Quonsets entered agricultural service by 1950. These structures remain visible today across rural America. Drive through Iowa, Kansas, or Nebraska, and you'll spot curved steel buildings serving farms for 75 years. Many show modifications, ventilation additions, concrete floors, door enlargements, but the basic Quonset structure persists, still functional 3/4 of a century after manufacture. Small businesses discovered similar utility. Post-war suburbs needed commercial infrastructure immediately. Traditional construction required time and capital most veterans lacked. A surplus Quonset costing $100 or $300 provided instant business space. Welding shops, auto repair garages, small manufacturing operations, storage facilities, all operated from adapted Quonsets. Some communities' entire commercial districts consisted of repurposed military buildings through the 1950s. Religious congregations facing space shortages purchased Quonsets as temporary churches. A congregation could buy a structure for $200, assemble it with volunteer labor over a weekend, add a cross and simple altar, and hold services the following Sunday. Hundreds of these Quonset churches operated across America through the 1960s. Some denominations used them permanently, others as temporary facilities pending traditional construction funding. The architectural profession initially dismissed Quonsets as wartime expedients beneath serious consideration. However, younger architects recognized important lessons in that curved steel form. The Quonset demonstrated that prefabrication worked, standardization enabled affordability, and speed didn't necessarily mean inferior quality. These principles influenced post-war prefab housing movements. Buckminster Fuller's Dymaxion house designs drew direct inspiration from Quonset construction philosophy. The Lustron all-steel houses, 22,000 units manufactured between 1948 and 1950, applied Quonset principles to residential construction, factory manufacture, standardized components, rapid assembly. While Lustron ultimately failed commercially, the concept persisted in mobile homes and modular construction industries. Internationally, Quonsets spread wherever American forces served. Britain retained thousands for village halls, sports facilities, and community centers. The Philippines converted Quonsets into schools and clinics. Iceland's NATO installations operated from Quonset structures into the 1990s. Australia used surplus Quonsets for rural infrastructure through the 1970s. German barracks, by contrast, mostly disappeared. Allied bombing destroyed many. Post-war reconstruction dismantled others for materials. Some remained operational for occupation forces, but few survive today, except as historical sites or military museums, monuments to an engineering philosophy that couldn't adapt to industrial warfare's demands. The Quonset's influence extends to modern military operations. Contemporary deployable shelter systems use advanced materials, aluminum replacing steel, synthetic insulation replacing fiberglass, computerized climate control. But fundamental concepts remain unchanged: prefabricated sections, rapid assembly, complete portability. The current military shelter system traces directly to that 1941 breakthrough at Quonset Point, Rhode Island. The Quonset hut story illuminates broader principles about technology, warfare, and engineering philosophy. The German and American approaches represented fundamentally different solutions to identical problems: massive military expansion across vast geographic scales under extreme time pressure. German engineering emphasized quality, durability, and traditional craftsmanship. Wehrmacht barracks, built in 1936, remained serviceable in 1945 and beyond. Brick walls, slate roofs, and concrete foundations provided structures lasting generations. This approach made sense in peacetime military planning, where infrastructure investments yielded decades of service. However, total war operates on different economics. Wartime infrastructure needs service life measured in months or years, not generations. A building serving perfectly through a 5-year war that takes 6 months to construct represents wasted time. A structure lasting 3 years but assembled in 1 day proves more valuable. American engineering accepted impermanence as acceptable trade for speed and flexibility. Quonsets weren't built for eternity, just for victory. This pragmatism enabled rapid response to changing operational requirements. Bases expanded immediately after island capture. Supply depots relocated as armies advanced. Medical facilities deployed within artillery range. Traditional construction couldn't provide such flexibility. The cost differential deserves deeper examination. Each Quonset's $14,000 savings compared to German barracks represented enormous military purchasing power. Across 160,000 Quonsets, accumulated savings totaled $2.24 billion, equivalent to funding approximately 30,000 M4 Sherman tanks, or 75,000 Willys MB Jeeps, or 15,000 P-51 Mustang fighters, or 400 Liberty ships. These weren't hypothetical savings. Money not spent on elaborate barracks bought weapons, vehicles, and ships that won the war. The Quonset's simplicity directly funded combat capability. Transportation efficiency multiplied these advantages. Shipping one Quonset required 1/4 the cargo space of conventional barracks materials. This efficiency freed shipping capacity for ammunition, food, and fuel, the substances combat units consumed daily. The U.S. Army calculated that Quonset adoption saved approximately 3 million tons of Pacific theater cargo capacity between 1942 and 1945, equivalent to 150 Liberty ship voyages or 6,000 ship days. Labor efficiency proved equally important. Wehrmacht construction consumed skilled craftsmen needed elsewhere. Every carpenter building barracks represented one fewer combat engineer constructing field fortifications. Every electrician wiring buildings couldn't repair battlefield communications. Quonset assembly required 0 specialized skills, freeing qualified personnel for tasks only they could perform. The Wehrmacht's construction system proved excellent for peacetime, but couldn't scale to total war's demands. Material shortages, labor shortages, and transportation constraints strangled their methodical approach. By 1943, Wehrmacht construction timelines stretched from 6 weeks to 12 weeks or longer, as the logistics system collapsed under impossible demands. American production, conversely, accelerated as the war progressed. The 1944 Quonsets were better than 1941 models: improved insulation, stronger panels, faster assembly. while costing less because manufacturing processes continuously improved. Ford Motor Company applied assembly line principles learned from automotive production, reducing assembly time from 16 hours in 1941 to 12 hours by 1944. This manufacturing flexibility exemplified American industrial advantages. The same factories producing Quonsets could and did produce aircraft components, ship parts, and vehicle assemblies. The same workforce assembled different products as priorities shifted. German industry, optimized for precision manufacturing, struggled adapting to rapidly changing requirements. The strategic impact appeared in operational tempo. American forces established new bases, expanded existing facilities, and relocated entire installations at speeds that bewildered German intelligence. When B-29 bases appeared in China seemingly overnight, Japanese planners kept bombing construction sites that were already operational. They couldn't believe bases could activate so quickly. The lesson extends beyond World War II. Modern military operations employ the same principles: rapid deployment, minimal logistics, maximum flexibility. Today's containerized housing, deployable hospitals, and expeditionary bases all reflect concepts proven by that simple curved steel structure from 1941. Sometimes the optimal engineering solution isn't the most elegant or most thoroughly crafted. Sometimes it's simply the one that works fast enough, cheap enough, and reliably enough to accomplish the mission. The Quonset hut proved this principle decisively. It wasn't beautiful, it wasn't permanent, but it helped win history's largest war.